this video, we're going to talk about how the oceans came to be. But in order to get there, we're going to start 4.53 billion years ago. 4.53 billion years ago, Theia collided into Earth. The resulting molten debris of the collision then coalesced to make the moon. The collision of Theia served as a great reset, blasting off the planet any volatiles such as water that had accumulated near or on the surface, and turning any surface that had hardened back into molten rock. Indeed, prior to Theia's collisions, it's thought that seas had already formed at the polar regions. After Theia's collision returned Earth to the molten state, Earth again hardened, with smaller collisions returning local regions of Earth back into molten rock, like Theia did to any parts on Earth that had frozen out. But never again would Earth be entirely molten. As the surface hardened, it produced minerals, which came together to produce rocks. At first, the hardening surface produced peridotite, making Earth's first and unsustainable mantle. Peridotite, which is denser than the magma upon which it was riding, fell in and partially melted. From the partial melt of peridotite, a less dense magma was born, some of which rose up and came to be the Earth's first actually stable surface, the basaltic crust that's beneath all of the continents and makes up the ocean floor. But even once the basaltic crust rose, there were no continents and there were no oceans. But both the continents and oceans were actively in the process of being made. It's the oceans that we're going to now take a look at, and we're also going to give a glance at stage 3 of mineral evolution, which started a little before the making of the oceans. It started out with the freezing out of the crust, and it comes to a close with the making of the oceans. Like the video, subscribe if big history is for you, and consider supporting my work on LiberaPay if you consider it valuable. Earth, shortly after 4.53 billion years ago, is now a black planet, with a crust composed of basalt covering its entire outer layer, and molten lava shooting and pouring out in some places, and adding further basalt. By 4.4 billion years ago, Earth looked very different. At that point, Earth was very likely a blue world. And if it wasn't a blue world then, it was almost certainly a blue world by 4.3 billion years ago. To understand how that happened, we need to take a closer look at the magmatic material that's making its way up to explode to the surface. Turns out that magma is enriched in all sorts of things, including water. Plenty of water and carbon dioxide are in the magma making its way to the surface. The water and carbon dioxide lower the melting points for the rocks, and this makes it that the magma is more liquidy. In fact, it's soup-like, causing it to ascend even faster. These fluids in the rocks that are making their way up are concentrated in all of the atomic types, all of the elements that don't easily join together in the silicates that make up the peridotite and the basalt that soon can be beneath it. So lots of elements find themselves in concentrations that are far greater than their average in Earth's crust. Elements like lithium, beryllium, boron, sodium, chlorine, fluorine, sulfur, potassium, gold, silver, uranium, as well as many others. All of these are going to come to form many more minerals than had existed prior to this. But it's the water itself that it's going to come to make the oceans. As the water makes its way to the surface, the liquid water phase shifts to gas close to the surface, which increases the violence of the coming explosion at the surface. And when that explosion happens, the volcanic vents release lots of volatiles and steam, with vents across Earth releasing millions of tons of nitrogen, carbon dioxide, and water vapor daily. The atmosphere was dense, and the weather was much more violent thanks to the much faster spin of Earth at the time. As the gaseous water molecules rose, they grew cooler and returned to their liquid state. H2O, or water, is somewhat unique in its polarity. It's a polar molecule, which means that it's charged positively on one end and negatively on the other. So on the oxygen side, it's charged negatively because the oxygen has more protons, so it's pulling the electrons of the hydrogen closer to it, and the hydrogen is pulling the electrons towards it, so that also ends up with the two hydrogens having a slight positive charge from their proton. Without this fact, water in the atmosphere wouldn't condense into raindrops, because each molecule holds the next more tightly thanks to this electric charge. The positive side of the molecule will attach to the negative side of the molecule, and then again. And this is important because water forms droplets that fall on the ground and make oceans instead of merely hovering around as a mist. This polar quality of water also affects the interactions that water has with the Earth once those first condensed raindrops fall to the ground. The first fallen droplets fell on a hot, thin crust of basalt, and the whole world enters the sauna epoch as steam rises from the water getting heated by the basalt all over Earth. But as more water falls, the Earth gets cooler and cooler, and we go from puddles to ponds to lakes to seas, and eventually a near globe-encircling ocean about 1 kilometer in depth. For the first time, rivers etched valleys, and the waves eroded the volcanic cone islands sticking above the surface. The eroded rocks formed sandy beaches and deposited wedges of nearshore sediment. The ocean came to cover almost the entirety of the globe because of the flatness of Earth at the time, which would continue to grow less flat across time as the continents built up. Likely by 4.43 billion years ago, and almost for sure by 4.33 billion years ago, our planet, Earth, was blue. And now let's take a look at the mineral situation. All of this water formed many new minerals. Many minerals formed from water evaporating and leaving minerals behind, like halite, or minerals that allow for water to atomically join their structure, as well as other minerals that water creates or enables the creation of. These minerals come together with the minerals that were formed in the formation of peridotite and basalt, the making of our first crust, and they increase the count from the 250 minerals that we had at the end of the stage of differentiation that fall to us from space, and that comprised Earth prior to the freezing out of peridotite, and now we're up to 500 total minerals. But just as with peridotite before, which partially melted, and from that partial melt arose basalt, so too the basalt is melting, pending. See you then.